I'm very glad to introduce the man who needs no introduction, Vitalik Buterin. He's involved in this camp since day one. He started ETH1 at the time, and now he's starting ETH2. And this is sort of a state of the nation that we get to occasionally, and where things stand on this rapidly evolving project. So please go ahead, Vitalik. The screen is yours.
Okay, great. No, I guess I guess even though the talk is on layer 2 day, this is this is still going to be fairly layer 1 oriented. But I mean, I think it's still important. Layer 1 and the layer 1 and layer 2 have a lot of kind of interactions with each other, and especially some of the stuff happening with sharding is going to be very relevant for any layer 2 projects as well. So this is just going to be a I guess a general summary of some of the well, I think at this point, all of the big ideas that are going into the longer term future of Ethereum. So like, I think we've talked a lot both in these workshops and in lots of other places about proof of stake, about Ethereum's specific implementation of proof of stake. And here we've talked about some of the other things like EIP 1559 a huge amount as well, but I want to kind of step back and also talk about longer term things that realistically are going to happen somewhere between like maybe 1 and 5 years from now, or even longer, and some of the technical challenges involved in that. So just a quick recap of the near-term future. Right. So what we already had is we had the Genesis, which was the launch of the proof of stake chain. We had the Berlin hard fork on the proof of work chain. Next week, we're going to have the London hard fork, which will actually introduce EIP 1559. Shortly after, we'll have the Altair hard fork, which is the first hard fork on the proof of stake chain, and the last hard fork before the merge on the proof of stake chain. And that's just some general efficiency improvements, but also it allows us to test out the hard fork mechanism, make sure that like actual users are actually capable of downloading hard fork code and that everything works correctly. Then after this, of course, we have the merge, and the merge is when the proof of work chain stops existing, and the applications, the state transitions that are currently on the proof of work side move over and happen on the proof of stake side after the merge. And so after the merge happens, like, well, what is the longer term future? Right. So one thing after the merge is that there's going to be this fairly boring cleanup fork. So the reason why this cleanup fork exists is that basically because there's a lot of demand and a lot of good reasons for the merge to happen fairly quickly. And so there's a lot of things that need to happen at some point around the merge that will end up happening after the merge to kind of fully do some just like some cleanup work that has to be done at some point after the transition to proof of stake. Like one example of this is removing the ETH data voting mechanism. The ETH data voting mechanism is a mechanism that the proof of stake chain currently uses to talk to the proof of work chain. And so after the merge, like this will just be the chain voting on itself, which is pointless. And so the cleanup fork will just remove that and replace it with direct access. Adding the ability for proof of stake validators to withdraw, fully, but hopefully moving the execution layer away from the current serialization, which is RLP, and moving to a somewhat better serialization. Potentially agreeing that clients stop trying to download the pre-merge proof of work chain, which could end up just allowing clients to do a lot of kind of garbage cleanup and just not bother to support older versions of the protocol if they don't want to. And then opcodes for accessing the beacon chain. So far, this is like, there's nothing super fancy and technical in this. It's just like fairly boring stuff that just has to be implemented. But after this is where the fun things begin, right? So sharding is the other big part of the thing that used to be called ETH 2.0. And now like we just call it proof of stake and sharding. And sharding is a scalability solution. And the way in which we are implementing sharding is somewhat, I guess, unique. And it's like basically the approach here is that we're starting off the shards in a very simple way. So we'll have 64 shards and they each have a block every slot, and the block can be about 512 kilobytes. And these shards will not contain transactions. So they will not have any kind of execution. They will only contain data. So this will just be 512 kilobyte blobs of data that will just be available, and the blockchain will guarantee that if a blob of data gets included on chain, then that blob of data actually is available. So it actually has been published. Now, I've talked a bunch in the past about how you can secure data availability in a scalable way. I mean, if you just like search data availability problem, I talk about this quite a bit, right? Basically, the idea is that instead of everyone needing to download all the data, you encode the data in polynomials, and so that if you have 50% of any piece of data, you can recover the other 50%. And then every node just randomly samples a few pieces and checks that all of the pieces that they sampled are available. And if all the pieces that they sampled are available, then with very high probability, at least 50% of the data is available. So in the actual rollout, we're likely to have just committee-based security, so just a randomly sampled set of validators vote on every shard, and then data availability sampling is something that will likely be added later. But there are already proof of concepts of this, right? There's already a proof of concept of sharding with committee-based security. There's a team that's quietly working on moving it forward. So I think this is something that will be go straight into a very intensive development stage as soon as the merge is finished. So the reason, now you might ask, well, what's the point of agreeing on 512 kilobyte blobs of data? So the answer here is rollups, right? So the rollups are a very powerful layer 2 solution because they don't just support a very limited number of transaction types, they support everything. They support like arbitrary VM execution, right? So channels do not do this. Channels only support payments, and channels have very high extra capital requirements. Plasma is very hard to generalize beyond payments and a few other applications. Plasma has withdrawal periods. Plasma has lower capital requirements, but if you want fast withdrawals, it has some capital requirements too. Rollups do not have any of those issues, but the trade-off that rollups make is that whereas channels like only put data on chain when you deposit and withdraw, and Plasma, aside from deposits and withdrawals, only puts O of 1 data on chain per slot. Rollups, they do put O of n data on chain for every transaction. Now, there is still a constant factor improvement, right? So instead of about 100 bytes per transaction, we're talking about like 12 bytes per transaction. And the computation of verifying those transactions is done entirely off chain. But for a rollup to be secure, you need to have this guarantee that the data in the rollup is available, right? So the data has been published in some medium where if it turns out that it's incorrect, or in order to check if it's incorrect, someone can actually go and download it if they want to. You know, they don't necessarily download it by default, but there needs to be a guarantee that they need to be able to download it on demand. And it turns out that like guaranteeing this data availability, even in the face of dishonest proposers, is hard, right? So like something like BitTorrent or IPFS is not a solution. BitTorrent and IPFS do not try to handle the case where the publisher of the data tries to equivocate and make half the network think the file is available and half the network think the file is not available. To solve that problem, you need some more advanced math, and like this is what we actually have. And so with a sharded chain, basically, instead of having something like one shard of basically theoretically up to about a megabyte of data available per second, we basically go up to 32 megabytes, or sorry, not per second, per slot. And we go up to 32 megabytes per slot. And furthermore, these 32 megabytes do not have to like compete with gas that's been allocated to or that's being used by other applications, right? So it's really just 32 megabytes per slot of data space, which is very powerful. Now, another fun thing we're considering is also staggering the shards. So having different shards publish blocks at different time intervals within a slot. And so you basically have a shard somewhere publishing every second. And this is one interesting strategy to allow rollups to be super fast if they want to. So this is the stuff that's happening with sharding, right? So once again, kind of like early stage here is to just have shards that contain nothing but data. And this makes it easier to verify. You can do data availability sampling. It means that you do not need any kind of fraud proof to do validation. All you need is to do the sampling procedure, and the sampling procedure is purely asynchronously safe. It doesn't depend on any kind of fraud proving assumption, which is very, very nice. But in the long term, there is a debate about whether or not we should ever add native execution in protocol to the shards. It's possible that will never happen, and it's possible that will happen like basically only when we actually have a ZK Snark verifier for EVM transactions, because if we have ZK Snark verification, then we can have execution within the shards, and that execution also does not need any fraud proofs. And so yeah, the whole thing would continue to be safe under asynchrony. But shards that do anything but just have data are, regardless of what happens, they're a very long-term thing. So this is data availability sampling. This is this technology that we're using to actually verify that data on shards is available. So basically, again, so you split up so you have these shards, right? So you have 64 shards, and then we have what's called horizontal subnets and vertical subnets, and these are like peer-to-peer subnetworks. So you can just think of them as being separate peer-to-peer networks. There's a peer-to-peer network for every shard, and then we have these vertical subnets. And the point of these vertical subnets is like this one holds the first chunk of every shard. This one holds the second chunk of every shard. This one holds the third chunk of every shard, and so forth, right? And these blobs are erasure encoded, right? There, in this case, 1,024 evaluations of a degree 512 polynomial. And so if 50% of any one of these is available, then you can recover and kind of republish the entire 100%. But the idea would be that you do each client does data availability sampling in a very easy way. They just join a randomly selected subset of vertical subnets, and they just download all the data on them. So this allows this basically means data availability is collaboratively verified client side. And so you have data availability guarantees, even if your honest majority assumptions on the committees that are attesting on these blocks are broken, right? So even if the consensus layer fails at checking whether or not a block is available, users can detect that blocks are unavailable and reject them. More security improvements. So one of them is the single secret leader election. So the idea here is that instead of right now in the current proof of stake, it's very easy to tell who the next proposers are for about 128 slots. And this poses risks. It makes it easier for them to collude. It makes them vulnerable to the denial of service attacks. So the plan that we have is to add a single secret leader election protocol. So a single secret leader election protocol is basically a protocol that chooses proposers for the next block, but in such a way that guarantees two things at the same time. The first thing that it guarantees is that only the proposer knows when they are a proposer. And the second thing that it guarantees is that there is exactly one proposer per slot. Now, it turns out that it's easy to guarantee one of those two things without guaranteeing the other, right? So to guarantee one proposer per slot, you can just pick one in the, in the clear. And to make proposers not visible, you could do what Purecoin did even way back in 2011 and basically just have each proposer or have each validator independently choose whether or not they are a proposer by just looking at private randomness. And like if they get lucky, then they reveal a hash pre-image and they reveal that they can be a proposer. But the problem with that approach is that statistically, about like whatever your slot length is, like about 36% of the time you're going to have no proposers, and about 28% of the time you're going to have multiple proposers. And so like however you do it, you either have to increase the block time for safety, or you have to just accept that you're going to frequently have block proposers fighting each other, which is a centralization risk because it creates an incentive to locate yourself in a powerful data center that has very good connectivity so you can beat out your competition. So Sego secret leader election is this fancy cryptographic protocol. The way that the implementations that we know of so far work is basically that every validator publishes their encrypted key, public key, and then the encryption algorithm is one that allows a zero knowledge or that allows an unlinkable re-encryption, right? So the unlinkable re-encryption basically says that like anyone can take an existing encryption and they can turn it into a new encryption of the same value, but there's no way for an observer to tell whether some new value is a re-encryption of some existing one that they know, or whether it's completely random. So the way that these protocols work is basically, or the way that encryption algorithm works is you take an elliptic curve, and that elliptic curve should not be pairing friendly, and you just choose 2 points. One point can be like, we'll call them, one of them can be X and the other can be R times X, where R is the value you're encrypting. And that just is the encryption, right? And then to reveal, you just reveal R, and then you can check it against the 2 points, and you know that you have an encryption of the correct value. And then the way that you re-encrypt is you take X and R times X, and you just multiply both of them by K, right? And so you have X times K, and then you have R times X times K, and that just still is a valid expression of the same format, except the points are different. So then what you do is you have a zero knowledge proof for a shuffle and re-encrypt operation, right? So basically there's an operation where someone just takes a bunch of the encryptions, they shuffle them while re-encrypting each one, they publish a zero knowledge proof that they did this correctly, and then you have an encrypted list of the same values except in some different order. And then instead of choosing proposers directly, you choose encryptions, right? And the only one that knows whether that they have a valid encryption is the proposer themselves, because they're the only one that know the secret number, their secret number. And if you don't have your secret number, then you have no way to tell whether, like, what any of the other encryptions corresponds to. So that's single secret leader election. This is also a kind of in the cards as a future Ethereum improvement. VDFs, verifiable delay functions. So these are functions that have the property that they take a sequential amount of computation time to compute. So you can't compute them more quickly by parallelizing. And whatever the output is, you can actually verify that the output is correct very quickly. So this is, there's a bunch of different constructions for this, but generally they all have to do with some version of like repeating a computation and then making a some kind of like special purpose quick zero knowledge proof of the fact that you did the computation correctly. And it turns out that that computation also has some kind of like mini trapdoor in it that allows making the zero knowledge proof to be faster than doing the computation itself. So we plan to use VDFs basically to add into the randomness and just make committee selection even safer, and to provide that randomness to applications that want to use it. Proof of custody is an anti-centralization technique. Basically, it's a mechanism that forces nodes to actually keep and validate data, or to perform some computational tasks. So like one example of this is if you sign off on a shard block, then you should also have to do this proof of custody calculation. And if you did it incorrectly, then someone else can challenge you, and they can slash you. So one, just the proof of custody that we're likely using is a very simple proof of custody. Basically, so let's say that you are attesting to a shard block. What you do is you run some specific computation on that shard block. So that could even just be like Ketchak hash the whole thing, could be whatever. And then if the result of that hash starts with more than, let's say, 80 bits, so 1 over 256 of the time, then you're not allowed to attest to it. So if it's, or sorry, when you make that hash, you don't just hash the block, you also hash like the block concatenated together with some secret that you have. So if the hash of the block together with your secret is less than some value, then you're not allowed to publish the block, or you're not allowed to attest to that block. And if it turns out that you did attest to a block, then someone later can make a proof of this. Like basically at some point in time, like say 2 weeks in the future, you have to actually reveal your secret. And once you've revealed your secret, then anyone can go and check that you did not attest to anything invalid. And if you did attest to something that you should not have attested to, then they can penalize you, and whoever caught you gets a reward, right? So the idea here is that it makes it basically prohibitively risky to attest to blocks if you haven't personally downloaded them. And so proof of custody can be used for, like, it's basically a general purpose technique for overcoming the validator's dilemma. And so we intend to use it in a lot of places. So that's security improvements on the consensus layer. Also, some things happening on the execution layer. One thing that we're considering is address extension. So increase addresses from 20 bytes to 32 bytes, both to preserve collision resistance and to allow room for version numbers and to allow room for some other things that we need for state expiry, which I'm going to talk about later. So this is all just one small thing that's being considered. The biggest challenge here is to just how to do backwards compatibility so that, like, say, new style addresses can hold balances of tokens where that token expects you to have a 20 byte address. So like basically figuring out how to go from here to there is the open research problem right now. Stateless clients. So this is something that we have been talking about for years and that we've been very excited about for years. The big thing that's happened recently that made them finally viable is Verkle trees, right? So Verkle trees are trees that are, instead of being trees of hashes, they're trees of vector commitments. And so each vector commitment can have a much larger size. So we're using size 256, and you can have a short proof that proves a whole, like basically every relationship between every parented child that you need in a proof at the same time. Right, so like in this diagram, if all you want to do is prove like this value horse over here and sheep over here, then you would have to provide the nodes going up to the root. But because the tree is base 256 instead of base 2, you only have to provide a very short number of them. Even in a really big tree, you'll only have to provide like maximum 2 or 3 of them. And then every one of these parent-child relationships gets proven with this multi-proof protocol. So Verkle trees massively reduce witness size. Compared to the status quo, they reduce it by a factor of 20 to 30. And compared to an optimal binary hash tree, they still reduce it by a factor of 6 to 8. So Verkle trees are very powerful. They allow witnesses to like basically finally be not that like or quite small. And this allows us to have clients that do not actually hold the state and instead just verify blocks by checking Merkle proofs. So block producers would still need to have state, but nodes that just want to verify the chain, they would not need to have the state. And so this makes it safer to increase the gas limit because even though increasing the gas limit increases the storage size, there would be fewer nodes that would actually have to do the storing. So that is stateless clients, which have been making a lot of progress recently. Okay, ooh, I have, okay, excellent, there's comments. Polynomial of degree 512 or 511, yes, good point. Degree less than 512. There really should be a mathematical term for this, right? Like it's the point, like the point is there's 512 coefficients, and like potentially the top one could be 0 by random chance as well. Do anyone have a link to that particular re-encryption schema? I think if you just search for single secret leader election on ETH research, I think you should be able to like dig through the links and find it, or potentially it's just listed explicitly there. Okay, Pradeeth Srikanti, I'm curious about post-quantum secure single secret leader elections. Yes, this is a definitely important point. I think realistically, yeah, we will, for that to happen, it is definitely important. The challenge is to basically how to allow this kind of third-party re-encrypting. And I guess something based on isogenies might be possible. I'm not sure there is a hash-only construction for single secret leader election so far. Actually, Justin, since you're listening and you're in the chat, do you know if there exists a lattice one? I mean, if there is, then that would be really nice too. Okay. So after stateless clients, state expiry is the next big thing that's happening. So state expiry is likely to happen after state Virtual trees, just because of the introduction of Virtual trees also does some cleanup steps to make it easier to implement. And the idea behind state expiry is basically state that was not accessed in the most recent 1 or 2 years gets moved out of the state that even block producing clients have to store. And so accessing that state ends up requiring you to provide, like the user to provide witnesses. So this is a more complete solution to the state problem. It basically says not only is it only some nodes that even have to store state, but also we're even going to very tightly bound the amount of state that even those clients need to store, and as a just constant multiple of whatever the gas limit is. So like even the state that clients store would no longer have to go up over time, which is of course really powerful for scalability. Account abstraction. So this is another one of those kind of things that we've been thinking about for a long time and excited about for a long time, but that are kind of like increasing in importance and increasing in, I guess, interest in putting serious effort into it. So the core motivation for account abstraction, and you can see it in the chart, right? Like basically, we want people to be able to use smart contract wallets and smart contract applications as first-class citizens. So basically, for people to be able to use smart contract wallets that do things like multi-sig or social recovery as easily as they can use regular externally owned accounts today. So the reason why this is hard right now is because today we have this rule that says that every transaction has to start at an externally owned account, and that externally owned account is the one that has to pay for gas. And then if you want to use a smart contract wallet, the transaction basically has to actually call into the smart contract wallet. This wastes gas, so it's not gas efficient. And it also has the problem that as a user, you have to have a separate ETH balance in the account that pays for gas, which is really frustrating. And if the gas price ever goes unexpectedly high, then you could also be stuck in a situation where even though you have a lot of ETH in your multisig, you don't have enough ETH in your gas account to actually pay. And like you basically get stuck until someone helps you, right? So it's really annoying. The way that existing smart contract wallets like Argent work is they basically just run their own relayer that kind of accepts users' transactions and sends them into the multisig. So with account abstraction, the goal would be to be able to send a transaction that just calls into the multisig directly or whatever the smart contract wallet is. And that smart contract wallet itself would also be able to pay for or directly pay for gas. In addition to smart contract wallets, another interesting use case of this is privacy preserving transactions. So things like Tornado Cash. Like basically, if you have coins inside of a zero knowledge privacy preserving thing, and you want to send people those coins, then you have the problem today is that you have to have some kind of ETH that's already in an EOA to pay for gas. And then the problem is, well, like, how do you actually get that ETH into that EOA without breaking privacy, right? Like, it's like, in order to withdraw, you have to already have withdrawn. So there's a bit of a catch-22. And the way this gets solved today is with a relayer market, but account abstraction can solve it much more kind of natively and robustly and efficiently. So there's two paths to this. One is to change the Ethereum protocol itself to support this. EIP 2938 is the latest in class proposal. And another alternative is to have a separate mempool. So, and separate miner logic for kind of accepting user operations as a separate type of object that represents calls. And then the miner just themselves kind of bundles those calls together into a transaction. So that was account abstraction. Ethereum virtual machine improvements, potentially looking at kind of what gets called EVMX. So EVM 384, but also just essentially modular math operations at different bit sizes. And this would support BLS curves. This would support other kinds of elliptic curves. It would support big number operations. So generally make the EVM more cryptography friendly, and potentially other improvements as well. So that's all for the near-term future. Okay, let me go back to questions. Right, so what do I mean by witness when I talk about statelessness or state expiry? Basically, I just mean if you have accounts that you did not access for a long time, then if you want to use those accounts again, you have to provide a Merkle proof for them. A Merkle proof that proves when that account was last accessed, and also a bunch of Merkle proofs to prove that it was not accessed at any, or it was not modified at any point after that. That's basically all it means. Post-quantum, do we need to rethink commitments? Yes, we basically have to switch to Fry, maybe there, which is almost a drop-in replacement for KZG. It's not quite a drop-in replacement for KZG because it doesn't have algebraic homomorphisms, which make things a lot of things really convenient. So, like, for example, Fry would not work as a replacement for KZG in the context of data availability sampling, because the protocol for generating all possible proofs in n-log-n time relies heavily on the algebraic homomorphisms. So for data availability sampling, we basically have to scrap the polynomial commitments and instead just have a direct Stark proof that proves that an actual Merkle tree is correctly formed and contains erasure-coded data. State expiry for coins in cold storage. What would change if no one wants to spend them for 2 years? Like, basically all that would have to happen is whenever you do end up wanting to spend them, you would have to provide one of these Merkle proofs. And this could easily be done automatically. Like, this could easily be done by archive nodes. It could be an API provided by Etherscan. It could be a service provided by some other kind of decentralized network. So there's lots of ways to make this easy for users. Okay. So the far future, right? So one thing that we're looking at is replacements for the current gas per consensus mechanism, which basically combines together LMD Ghost as a short-term fork choice rule with Casper FFG as a finalization mechanism. And one of basically the problem with current Gasper is that there's this complicated interplay between these two mechanisms, and there's various issues that come up because of the interaction between the two of them. CBC Casper is one alternative. It basically just makes the finality itself rely on LMD Ghost. There's also other alternatives, but basically just doing another revamp of the proof state consensus that incorporates everything that we've learned and just more thinking over the last couple of years. Snark everything. So basically just to use snarks to make everything in the blockchain self-verifying. So this can involve snarking the beacon chain and snarking the verifications that happen at the consensus layer. it can also involve us snarking the execution layer, which is going to involve snarking the EVM, which is a very difficult challenge, but there are multiple teams doing it. That could be done by snarking the EVM directly. It could also be done by snarking a VM that EVM code can be compiled to. But if you write new code, you could write new code in the new VM, and then it would be much more efficient to snark. So snarking the EVM makes the beacon chain node, or makes running a node much lighter. And potentially, if we want to add execution into the shards, it makes it much easier to do that. So this is something that's likely to be a major project over the next couple of years. And quantum security, right? So replacing snarks with starks, replacing BLS signatures with a Stark-based aggregate signatures, replacing the Verkle tree with a Stark Merkle tree. So like basically just replacing everything with some kind of post-quantum alternative. Most of the time, that's just going to involve Starks. Sometimes maybe that'll involve some isogeny or latticing, like for example, for the single secret leader election use case, but I get that's one of those areas that still requires more research. I think aside from the single secret leader election thing, like we know how to replace everything with Starks if we are assuming that Starks can be made fast enough, and of course that there can be enough audits on the mechanism and its security that everyone's confident that they work well. So at this point, like we're arguably done, right? So after these short-term changes and after these long-term changes, if Ethereum never gets modified again, then like that would not even be a bad outcome, right? Because from that point forward, like anything further could really be done at layer 2, right? Like you have enough of functionality to have what I call functionality escape velocity, and so if layer 1 just completely ossifies, then any improvement from that point forward can just be done through some layer 2 mechanics somehow. But there is still some room for layer 1 improvements, but layer 1 improvement is likely to slow down and be less ambitious after this, and because in the longer term, blockchains should focus more on like predictability and backwards compatibility, and it's in the short term, right, that Ethereum is in this phase where it's doing a lot of this very rapid and often very backwards incompatible innovation. So longer term, just kind of more settling down, more stabilizing, probably just ongoing upgrades to cryptography. And that is basically where Ethereum is kind of going to end up, I guess. Hopefully in 5 to 10 years, we'll see. But I think the things that I talked about there are definitely like the major things on the consensus layer roadmap. There's also not consensus layer things that are happening and that are going to happen, right? So like, for example, Piper and Jason Carver and some other developers at the foundation are working on the Portal network, which is a more efficient way, a kind of decentralized way for users to access history. Another thing that I did not touch on at all here is light client protocols. After Altair, there will be an efficient light client protocol for verifying the Ethereum chain. So that my hope is that will help us say goodbye to inferior centralization, or at least to inferior trust dependency, but we'll see how that goes. And then there's some other small things, like we'll have to have a protocol for providing history. We'll have to have these protocols for providing state. A lot of the infrastructure for making like cross rollup transactions and all these layer 2 protocols will have to actually be built, but that's kind of higher layer, right? So this is more consensus layer things. Does anyone have more questions? I'm happy to answer lots of questions. Okay, Remco Michaels, will Ethereum become a privacy coin in the end? I mean, Ethereum's a general purpose platform, right? So there are multiple projects trying to build privacy systems on top of Ethereum. So Tornado Cash was the simplest one, but there's more advanced ones like Aztec, for example. I expect those will continue to exist and continue to be built and continue to get better. I think Ethereum as a whole turning into a privacy system, that's less realistic because there are unavoidable trade-offs with becoming a privacy kind of a system. Like particularly you have to have someone that has encryption keys for something to be private. There needs to be someone that actually has the information and no one else can. And that doesn't really work well with applications like Uniswap, for example, where there's no one that can have the keys, right? So something like Uniswap, it's much harder to see how it can become fully privacy preserving. So I think Ethereum is going to continue to be this general purpose playground, and there will be privacy preserving things built on top of it. And there are probably going to be some applications that won't be privacy preserving. If academic folks wants to get more involved in ETH2, best way to get hands-on involved. Following threads on ETH research and contributing to threads on ETH research is definitely great. Also, reach out to us. I know a lot of us are very open and friendly to and happy to talk to people. Also, I just talked about what some of what the kind of the listing of our challenges is, but there's also more detailed documents that talk about what some of those challenges are. I can probably find those at some point. So I guess pick a piece of Ethereum, analyze it. If you discover something interesting or discover a way to improve it, then we're always very happy to hear that. The challenge of cross-layer 2 transactions. This is an interesting one. So I think there's a couple of challenges here, right? Like one is that if we're talking about optimistic rollups, then so in either case, in optimistic rollups or ZK rollups, doing cross-layer 2 transactions the naive way basically requires withdrawing from one layer 2 and then depositing into another layer 2. And the problem with that is that requires transactions to happen on layer 1, right? And so that process is potentially very expensive. If we're talking about moving out of an optimistic rollup, then doing it naively becomes even harder because you have to wait a week for the fraud-proof window to pass by. So I think if we want layer 2 cross transactions, there's all you want to do is move coins around, then I have a proposal that's on ETH research for how to do a decentralized exchange between rollups. If you just just search decentralized or cross layer 2 exchange, you'll probably find it. The proposal is quite clever. It even only requires one of the 2 rollups to actually be smart contract capable. So the other one can be just like a pure coin sending rollup, and it can still work. So that's. But transferring coins around is a very application specific thing, right? If you want something that's less application specific, then you might have to you have to start thinking about questions of well, what happens if it comes from an optimistic rollup? What happens if it gets reverted? Now, I personally do think that 5 or 10 years from now, all the optimistic rollups are going to convert to ZK rollups. Because ZK tech is just going once it gets good enough and once it gets sturdy enough, you just want to use it because you don't need any withdrawal delays. And then once you have ZK rollups, then it gets easier, right? Because you can make a transaction that basically creates a receipt on one rollup, and then you can make a proof of that and import that proof into another rollup, and then you can verify that proof inside of the rollup. So do things that are very similar to cross-shard communication, but just have it be cross rollups. But it's just a lot of infrastructure that actually has to get built. EVMX, basically, the idea here is to just add support for modular arithmetic, so modular addition and modular multiplication for at least 384-bit numbers, but ideally a number of bit sizes. It would be nice to have 128, 256, 384, 512, maybe 1024 and 2048, and up to 4096 as well. And the point of this is to just make Ethereum more cryptography friendly. These operations, they would also be in like Montgomery operations, so they would actually be pretty close to optimal to actually use. So the point is to get to the point where cryptography implemented in EVM is within maybe a factor of 2 as efficient as cryptography implemented natively for as much cryptography as possible. And this would allow us to avoid the need to add more precompiles and potentially even remove some of our existing precompiles. Cardano, I have admittedly not been following Cardano closely, so unfortunately, no, sorry for the ADA apes here. Unfortunately don't really have too many things to say, but I don't know, maybe I'll look into it at some point and I'll have more comments in the future. Polkadot, I guess, I mean, a lot of things in the Polkadot design are definitely similar to the Ethereum design. The differences are fairly kind of detailed and subtle. Like they have to do with things like we have shards and roll-ups, but they have a more enshrined concept of parachains. They have a different auction scheme for allocating a parachain, whereas in the ETH2 sharding design, you're able to like basically just spin up a roll-up and it can use like as few or as many blocks as it needs to take. And then there's another big philosophical difference between Ethereum and Polkadot is that Polkadot people love on-chain governance and Ethereum people generally do not love on-chain governance. If you want to find out why I don't love on-chain governance, if you go to my blog, vitalik.ca, and just like go to the governance section, then I have some posts where I explain what my concerns are. EWASM, I think realistically, EWASM has been deprioritized a bit because we just realized that the hopes that we had for EWASM being fast enough to avoid the need for precompiles did not really materialize. There are other advantages to EWASM, but the advantages are relatively smaller, and so like it's less value for effort than pretty much everything else on the roadmap. Another example of the effort that EWASM would provide is that we would have to either permanently maintain support for both the EVM and EWASM, which would be really terrible. It would double consensus complexity, or we would have to basically take existing EVM code and force compile it into EWASM somehow. So there's challenges there. Right, potentially rollups could use WASM internally. That's excellent point by Justin. High level effects of ETH2 on MEV. I think so. Proof of stake by itself, not too much on regular MEV. The biggest effect is like there was this paper I wrote with or this post I wrote with Georgios a few days back that talks about how the more like the very hostile forms of MEV, like reorg attacks, become much more difficult after proof of stake because of how the fork choice works. Otherwise, probably not too much. How can someone without a coding background, like an MBA with background in finance, get involved or contribute to the crypto space? I think there's a lot of paths. Like I think, like first of all, you could just like join either a DeFi project or some other projects building on Ethereum and participate in that project in a non-coding capacity. I think that's a totally fine path to take, and lots of people have it. You probably should. Address extension, is it expected in the near-term future? It seems like a lot of work. I agree, it's a lot of work. So this is part of why we're doing Virtual trees first and state expiry second, because state expiry does depend on either address extension or some alternative. And so that gives, like doing Virtual trees first gives us more breathing room to figure everything out. So none of this stuff is going to be happening the next year, right? Because for the next like at least half year, we're focusing on the merge. But after that, we'll see. What are my thoughts on this prognosis? Speculation will eat available capacity. Therefore, Ethereum will only ever enable speculation-based apps. I don't think that's true. I don't think induced demand is infinite, right? Like I think there is going to come a point where, like basically the way that I think about it is like there is some kind of like cosmic microwave background level of gas usage that that I sometimes call it. Like there's gas usage that just happens based on just applications that have an almost unlimited demand for space. Like one example of this is if the gas price was like 50 Wei, right? So like not even 50 Wei, it was just 50 Wei. Then like I would use Ethereum to store encrypted backups of my hard drive, right? And like I think lots of people would. And then going above 50 Wei, you could use it to store encrypt. Like even if the gas price was like 5,000 Wei, people might be willing to use it to store encrypted backups of other things. And then going up higher, you have like Uniswap arbitrage. Like people might want to make Uniswap arbitrages of every single token in response to the tiniest price movement. And then like going up and up, like there's all of these use cases, right? And like you can think of that of this kind of cosmic microwave background usage as a demand curve, and or sorry, yes, as a demand curve, and it intersects with the supply curve somewhere. And if the supply curve, like if the block space goes higher, then the equilibrium is going to be lower, right? And any application that's willing to pay more than that level is going to be able to survive. I think the reason why in this argument that like speculation will just keep eating capacity, whatever it is not correct, is because if that is correct, right, then like we're basically EIP 1559 is going to turn ETH into insanely ultrasound money like the world has never seen, right? Like for example, at the 15 million gas level, in order to fully cancel out proof of work emissions, you would need something like you need a gas price of 133 Gwei, right? And then post proof of stake, then that goes down to something like 10 to 20 Gwei. But then if, let's say, imagine we add some scalability and we go up to having 1 billion spendable gas per block available somehow. But let's say the gas costs stay at 20 Gwei, right? Then we have 1 billion gas per block multiplied by 20 Gwei. And so we're talking 20 Gwei per block, which is 2.5 blocks per year. We're talking 50 million ETH being either burned or directed to some kind of treasury fund if it's a layer 2 protocol every single year. Like if we live in that world, then that's like an awesome world to live in if you're a holder of like either ETH or one of these layer 2 tokens, right? And so like burning literally half of the supply every year, like that's just obviously so unrealistic. And so just from a point of view of pure arithmetic, it has, I think gas prices have to go down at some point. Let's see. Can the ETH2 chain be viewed as a public bulletin board for cryptographic primitives? When data availability is only verified right after a block is mined, there seems to be a little incentive to keep a persistent storage. Okay, so I think, so there's a few levels of incentive to keep persistent storage, right? Like one of them is that you have to publish the data in real time for to pass data availability checks. The second is that for a short period of time, maybe about 2 weeks, you have to keep the data around because you have to pass proof of custody checks. And then for the longer term, then the incentive to keep data around is basically the possibility that like someone will want that data and they're going to be willing to pay for it. I mean, potentially, if desired, like that, you could even add an incentive into the protocol and just like have the protocol itself kind of randomly poke around for history to incentivize ongoing storage. But that's like only if people become really concerned about this problem. I personally am not that concerned about the risk of data being completely lost. The reason is that even with these numbers, like we're talking about, I think it was about like 1.5 or 3 megabytes per second. Like that's still only about like, how much was it? Like in the tens of right, it's in the tens of terabytes per year, right? So if it's in the tens of terabytes per year, then like that is something that if someone wants to, they just have to like keep on buying a hard drive once every couple of months, and one person could still back up all of Ethereum if they really wanted to. So it just takes one hobbyist, even with the extra scalability of sharding, and the data is going to be around somewhere. I mean, I think the block explorer providers are definitely going to do it. I expect even like groups like the Internet Archive might be interested in doing this sort of thing eventually. So I think there's a lot of people that will be willing to back up that amount of data even in the long term. And then another thing is that if you're if you want to use the ETH2 as a bulletin board for a specific application, then you don't have to care about the entire data in the long term. You just have to care about the portion of the data that applies to your application. And so the amount that you have to store is much less. Let's see. What are my thoughts on Ethereum becoming much harder to split or hard fork because of DeFi? Because, like, for example, USDT will only be valuable on one chain. I think it's a good argument, and I think like hard forking is definitely turning into something, or contentious forking is definitely turning into something that's like that looks more like nuclear deterrence than it does like a peaceful split. And like that definitely has downsides to it, but that's also unavoidable to some extent. Let's see. How does a malicious staker compare to a malicious miner? What can and they cannot do? So there, the answer is that unlike proof of work, where a 51% majority can just keep on do reorgs of arbitrary length with no in-protocol penalties, in proof of stake, if you do a reorg of arbitrary length or of more than a few slots, then you get slashed and you lose a huge amount of ETH. So that's the biggest difference. What future do I see for Proof Humanity? I think it's great, and I think I'm definitely hoping even more Ethereum projects adopt it. Let's see. And yay, I caught up to the questions. Okay, amazing. I don't know. I mean, I'm happy to just leave the rest of the time for Justin to talk about things.